So this is a continuation of Thursday's lesson on tolerancing, and what I've done here is I've updated the pins and the holes with 3 pins and 3 holes, and that's just so I can show you some differences between what's called a cumulative tolerancing. Let's go over to this drawing, and the other kind of non-accumulative tolerancing. So this is a representative. This is the top. Let me just show you. This is the holes. Here you can see it's the holes, right? And this one here is the pins. Drag that around. There we go. You can see it's the pins. Okay, so I'm going to Control Z for both of those. Control Z for the South Africans. Okay, right, so I've deliberately this time, instead of what I did on Thursday, I've deliberately made these holes asymmetrical as far as the vertical axis is concerned. So if I were to put in a center line between there and there, you can see that it's asymmetrical. Okay. Alright, so I'm going to start as always with the datum, so that would be a single datum there. I'm going to change that to an A. Just go with an A, right? Didn't do it. Another datum over here, which we'll call B, hopefully. Yes, we do get B. And this one we'll call C or D. So that should be D, because we've used the other ones up. Okay, so primary, tertiary, or the other way around, it's not going to affect us too badly here. So cumulative tolerancing happens like this. If you start from a point, it doesn't have to be a datum, and you go like that, right? And then you continue your datum from the previous point to the next point, and then you continue the next dimension from the last point. So you're accumulating the dimensions. So I'm going from one to the next. Okay, and these are currently set at configurations which show the difference. So I'm just going to quickly hop over and go to my let's see if this will do it. Is that 37? I'm going to make sure I have the right one. That's ideal. So I actually want cumulative. There we go. Okay, and this one here as well. So these are, as I mentioned before, I think these are configurations that you can set up. So I'm actually going to get rid of these center lines just because they're not going to help us. Okay, so we're starting with a base point of 25, 70, and 75. 25, 70, and 75. So if I added to this, I'm going to click on here, go to this pop-up dialog box, give it a symmetric tolerance. I'm going to select 1 as always, just to illustrate. Okay. Now I don't want to go and do all of these one by one, so I'm just going to grab this nifty little tool called, if I can find it, Format Painter. So I want to copy what happens there and just apply it to all of these others. So they've all got the same tolerances. Okay, so if I were to take this seriously, then that dimension would go in a range from 24 to 26. Okay, and this one here would be from what's that, 70, so that would be 69 to 71, right? And similarly this one would be 74 to 76 to take those off. Okay, so the bottom figure here is just to show what the tolerance effect would be, what you'd actually have. So let me just see if I can do this format painter thing again. So I want that to be copied across. No, let's try that again. Format. From there, I want it to be. No, it's not going to do it. Never mind. I think these will cover us for now. You'll be able to see. I'm going to use those figures just to illustrate what happens here. So I've set this. I set these. What do you call them? Configurations up to show the minimum and the maximum. So here we've got 69, and here we've got 74, and there we've got 24. So that's the minimum. Position dimension. In fact, I need to also dimension this, which is 27, and that should be 26. Okay, so those will also be, as with the others, give us a symmetric tolerance of 1. Control, if it's not doing, there we go. So just select symmetric. I could have used format painter there, I should have. Alright, so that's the geometry and size, and then these are the positions. So if I go, this one's at its minimum, so 24 plus 69 plus 74. Let's go to this view here and just change that to the error one, cumulative error. Okay. And now if I overlay the one over the other, you can see what sort of huge tolerance problems we've got. So you can see that even on the first hole, although this is exaggerated, it might not be too bad if we brought these down. So, okay, quick edit there. I quickly changed these, the hole in the pin, so that would have been 27 plus or minus. So this would actually not be plus or minus 1. It could be 27 plus or minus, and 27 plus or minus. But I've just left the tolerance in here, so that's actually 27 just on its own. That's not going to work. Right, so just to overlay the two, so in other words, realistically, you should be able to fit the one inside the other. Not quite. But you can see how large the error is here. If I were to do an overall dimension between this point and that point, 167 on this one, and on this one here will be 173. So that is a full 6 millimeters error that happens because of the way I've dimensioned, like I have here. If, however, I change the way I've dimensioned this, so I'm just going to change the configuration here so that the dimension will reflect what I'm actually getting at. Okay, so I'm going to delete these 1, 2, 3, and those. You can see the way that I've set it up. These two dimensions are instantly now meeting one another. So if I do a proper dimensioning, which is from a datum line, which in this case is D, to that position, and the next one is back to the datum line to start, and then to that position, back to the datum line, and so forth. Well, I already got that one in there, so I don't need it. Now you can see that the tolerances are not going to be nearly as strongly, well, they're not going to accumulate in the same fashion. So if I go from there to there, we've got that already. If these were to have plus or minus 1 millimeter, let's just add that in. So quickly go to our little control box, symmetrical, give me 1 millimeter, right, and format painter, so we don't have to do all this work. Need that one changed, that one, that one. Okay, a quick edit. I've updated this. So these don't reflect they don't have the tolerances in them. These are the actual dimensions once they've been tolerant. So this is at the extreme of the one limit and the extreme of the other limit. So that's the extreme maximum positional limit with the extreme size, and that's the extreme minimal position limit with the extreme size. So let's see what happens when we overlay the one over the other. So you can see that that's a much better fit. There's a problem here because the dimension that I chose or the tolerance here of plus or minus 1 is just too large to accommodate this. So I'd have to adjust that downwards. But you can see that the error on each one of these, the interference on the left-hand side, would be the same, which is completely different to what we had with the accumulative tolerancing. So that's what non-accumulative tolerancing or dimensioning from a datum achieves for you. I'm using exactly the same tolerance limits. I'm just selecting the datums as the starting point, and so that limits the amount of error that I can encounter. Okay, so hopefully that explains why dimensioning from datums is so important. I'm going to hop over now to this sheet, which has some drawings on it, where instead of having, well, in this case we've got the holes and the pins are symmetrical around the center line, and I just wanted to illustrate a little bit of what happens when we do that. So over here is my my starting point. These two are just the results. So if I just dimension across from here to here, 140, right, and if I give that a, say, symmetric tolerance of 1, then the effect is, well, let's just quickly add these in as well. So let's give that a symmetric tolerance as well of also 1. So these will all be 28 from 26 to 28 millimeters, and the reciprocal ones will be somewhat smaller. Okay, all right. So that's yeah. Essentially, that's, I think this here is. Let me just see what it is. Not doing it the way I want. Chose the wrong one. Just Control Z, go back. Right, so select the sheet one, then I should be able to, so that's the holes, okay. Right, so this is holes, and that is pins. So the pins will obviously always be smaller than the holes because they need to fit in, and you can see if I fit the one over the other, that at the maximum and minimum conditions for those two different parts, the pins at their smallest, or is that their largest? Can't remember. Yes, at their smallest, but with the maximum position dimension, will actually fit into the holes which are at their largest, but with the smallest position. Pins at maximum, there we go. Didn't spell it correctly, let's just correct that because we're pedantic. Pins at maximum position tolerance and minimum pin size, and then the holes are at minimum position tolerance at maximum hole size. So in other words, those are the two extremes that you can have with these two parts. Okay, so that's eliminating even to an even better extent the amount of error that we looked at with the datum starting from a datum point, in this case where something is centered. Alright, so I was going to explain to you, or need to explain to you, how this geometric tolerancing command works. That is called a feature control frame. Okay, and that's FCF for short. So if anyone mentions FCF or feature control frame, you now know what it means. It's this geometric tolerance command. So this allows you to put a set of symbols which have certain meanings in directly onto a dimension and to alter what it does. So before I do that, I'm going to select this one here, 28 plus or minus 0.1, and with it selected, I'm now going to decide on what kind of tolerancing I'm going to need. So on Thursday I said I couldn't find the control position, or the position dimension. Here it is. All of the conditions you need are in this box. So straightness and flatness are very similar, as are circularity and cylindricity. We're only going to deal with those two sets for now, and then the position one as well. So I'm going to select, because this is just a flat piece. Flatness applies to 2D things, and sorry, not flatness. Yes, flatness. Straightness. Straightness applies to 2D things. So in this case, the moment I select the symbol, it gives me the list of possibilities at the top. So I can do a diameter, maximum and least material conditions, and these we're not going to worry about. So it's just these three for now. So in this case, I want a straightness with it won't have a diameter, it won't have a maximum, we just need a tolerance. So let's say we want to control it by about 0.2, and I'll explain how this works now. So the moment I say OK, it drops that box in next to this dimension. They should be together. Right, so they are actually together. So what does that mean? So I've drawn this box again on the right hand side. So this means that 28 is the height that this box can be, plus or minus 0.1. So I'm going to just visualize that. No, that's the wrong command. No, it is. It's the right command. By offsetting just this line. Just do that again. Offset that line. So I want it to go bidirectionally, and I want it to be construction geometry. Okay, and it says plus or minus 1, so then that's got 1 millimeter in there. So it could be 28, or sorry, it could be 27 or 29. Okay, and just to make this a little bit easier to understand, let's color these. So let's make those sort of a bright blue, and just make them a little bit thinner as well. Right. And so in this box, I'm going to delete this top line, and then I'm going to extend these lines. So I'm going to go a corner, extend the top line to that one, and then extend the bottom line to this one. So that if I took that tolerance seriously, ignoring what this box says, I could legitimately create a part, put a line that looks from the side like this, because 29, which is the height here, let's just dimension that quickly, is 28 plus or minus plus 0.1, and 27 on this side is actually 28 minus 0.1. So that's actually what you can get if you have this. What this box does is says, well, no, you can't do that. What you can do is you can go make that point, because that's 0.2, so 0.1 either side, or let's no, just 0.2 either side, I think. Let's make that 0.2 and that 0.2. Okay, so if I were to change this height to be 29, for instance. You can see that the amount of variation that I'm allowed because of this box is just the 0.2 either side. So I'm controlling the amount of flatness using this box. So it can go to 29 and it can go to 27, not a problem. But whichever one of those extremes I go to, or anywhere in between, I can always only vary the flatness by a total of 4, 0.2 and 0.4. So that's the maximum amount of deviation that I'm allowed there. Obviously, once you start getting into tolerancing a bit more, you'll understand that this line could waver between these two lines. It could go up and down, and that's what actually happens. So that's what we're doing with these boxes here. Let's do the same thing again with a circle. So let's draw a circle in here. Dimension it, give it about 50 diameter. Control C, Control V. Just line these up. Make those horizontal so you can see the difference. Okay. So if I want to use that feature control frame on a circle or any kind of round object, let's try and do that quickly. So, let's put in a tolerance in there. Symmetrical. Be consistent. Okay, so I can, according to this thing, I can offset that by a whole 1 millimeter, bidirectional. Let's do that again. That's what we do. So quick edit while I change the sound settings on my system to make it sound better. Hopefully this works. Right, so I want to add in a tolerance in here. So let's go up to this baby here, go symmetric. Okay, so now one of the things that I haven't shown you, which I've just discovered myself, if you want to change the tolerance here, if you want to say 0.4 for instance, you type in this little block, and then it actually keeps a record of what you've typed in. So I typed in 0.5. The reason I'm typing in 0.5 and not 1 is because we're actually changing the radius here, and that is a diameter. So if I put in 1 in here, plus or minus 1, we'd have a tolerance variation of 4, 52 and 48. So we can just check that now. Alright, so that's what we've got, so plus or minus 0.5. So let's illustrate what that means. Let's go to an offset. If we put 1 millimeter in, let's just show you what happens with 1 millimeter, just so that you believe me. So if I dimension this, you'll see that this is a diameter of 52, and that is a diameter of 48. That's a whole 4 millimeters variance. Alright, so you've got to be careful of that. Get rid of these. Don't want it. Don't want it. Let's do that again. Offset by 0.5. And that's what we're doing. Okay, let's pull these out. Make this nice and visible. Alter these to be a nice bright blue. Okay, and make them a bit thinner so we can differentiate. And it's done at this time, right? Okay, so before I put in the geometric tolerance, the feature control frame, let's pull that across so that we're reminded of its name. Before I do that, let's just examine what this actually means for circularity. So first thing I'm going to do is put in a center mark just to help me put in the next step, which is an ellipse. I know it's an ellipse because as I know it's an ellipse. Right, so an ellipse, you can go from the center to the outer circle as the x dimension, which would be 50 plus or minus, would be plus 0.5, so diameter 50.5, and then to the inner circle, which would be 49.5 millimeters, and that's, we've got our ellipse. So you can see that your circularity could vary by a whole 1 millimeter, and you'd get an ellipse, which is what happens in real life. You do get, nothing that you make is actually perfectly round. It all is slightly off kilter in some way. So there we go. Maybe let's make this a little bit thicker, just so that that's more visible. 0.5. There we go. Right. Maybe a bit too thick. Okay. So if I put in now a feature control frame, an FCF, and I select here circularity. We're not going to select cylindricity because that applies to 3D. This applies to 2D. And I just put in something like what if I put in 0.2? That's a whole 0.4 millimeters. No, that's okay. Let's try that. Right, so you see that's attached nicely. This is attached to that dimension. Hey, move. There we go. Just to show you. So that's what the circle is going to do. Maybe that's too, let's make it the other way around. Let's make it thinner. There you go. Right. Okay, so if we go across to the other side, and we now put in an offset of 0.2. So that's not that much smaller than the 0.5, but I think you'll get the point. So drag those out of the way. Color these nicely so visible, make them a bit thinner. Sweet. Let's see. The amount now of deviation in my let's put the center mark in the circularity is much less pronounced. So it's still going to be elliptical of some sort, but from there, hey, why are you not doing what I want? Center mark, give us that baby. From there to there to there. Okay, and so just on the dimension of 50, we can compare these. So obviously this can get bigger by 0.5, and I'd still be limiting using this FCF. I'd still be limiting how much it can vary in terms of circularity. So I'm going to now grab my two ellipses if I can find them. Let's see, that's why I color them, because then I can find them. There you are. Let's just color you quickly. Right, so I'm going to grab that one, say Control Copy, put it in here, and then go across to this one here, Control Copy, put it in. Oh, I think I copied the wrong, it's the wrong one. Control Copy. Okay, let's just get these to align if we can. Concentric, will they do it? Yes, they will. All right, so there we can see the difference between that's how much the circle could deform in this instance without the FCF, and on the right hand side that's how much it could deform with the FCF. Quite a mouthful. So that's the use of pull those down. That's the use of this in circularity. So let's move lastly to the position dimension thing. I'm going to replicate what I'd done earlier with a sort of a feature inside a block. So this could be either a pin or a hole. Quickly dimension this. That gave us a 2 mil little block. Okay, let's just get rid of that because that's a little bit of a secret sauce that's coming later. So that would be, if I had 43 plus or minus 1 and 33 plus or minus 1, I'd get a zone which was 2 millimeters square. So the limits of the zone would be these 4 corners of this square. So if I'm now going to apply a position FCF using the geometric tolerance tool, I'm going to go to symbol, I'm going to select this position one. You'll see there's a whole range of options available to you. So diameter is the one I want to choose. I'm not really going to deal with maximum and least material conditions in this thing. I'll explain what those terms mean. That's it. So I'm going to put in diameter, and then I just need to specify what kind of tolerance. So I want to put 2 in because that's what we've got here, but then that'll be wrong, and I'll show you why. Okay, so we'll put 2 in, so that's attached to this. No, it's not. It should be. Okay, let's pretend it is. Right, so that means that for the position given here, I want a diameter 2 tolerance zone. So that really means that I want a circle. So a tolerance 2 would be from that point to that point. If I measure that, that is a 2, diameter 2. Okay. Right. So, but that's not correct, because if we want the equivalent of what this little square gives us, we should be using the outermost edges of the square as the basis for our tolerance zone, because that's the equivalent. So I'm going to go from here to here, and that should give me a much bigger tolerance zone. It's 2.83. Okay, so I'm going to go back to this, double click on it. You should be able to edit it and just type in there 2.83. And that's what that means, that the tolerance zone is a whole 2.83 diameter and not the square. So it's giving you a significant amount more tolerance leeway whilst acknowledging that the limits are exactly the same as the square, because if you took that point and you distributed it equally in a circular fashion, that's what you get. You wouldn't get this little bit in the middle here. You wouldn't be restricting your tolerance to a square, which is unnatural. So that's what that's doing. It's giving you more leeway. So the way you can notate this is this can be attached to that dimension. I'm not sure why it isn't. Let's just try this quickly. Right, delete this one. See if this makes a difference. So we'll go to that one, diameter 2.83. Okay, still hasn't. Alright, well that you can just place next to the dimension or beneath it, somewhere in the vicinity, and that's actually connected to this. The other way you can do it is you can go to geometric tolerance and actually select your feature first. Go to geometric tolerance and do exactly the same thing. Diameter 2.83, and we say OK. And so that's doing the same thing. So that would be out here. We can move this if we want. So just want to move that to 35. So there we go. Now I'm telling whoever is going to look at this that for this feature, which is diameter 35, the position, you have a full circle of 2.83 tolerance to play with. And then these two, so I would actually delete this in this case, because those two dimensions would give the theoretical center point. So that's the end of that for now. Thanks for watching. We'll see you next week.